Hello everyone, myself Dr. Sunny Kumar. I am a assistant professor in Department of Chemical Engineering, PKG College of Engineering and Technology, Panipat. I am giving a lecture on unit process subject. This is a lecture number 4. In the previous lecture, we have discussed about uh, the different types of alkylation. So these are alkyl bonds to the trivalent nitrogen, alkyl bonds to the pentavalent nitrogen, and alkyl bonds to the metal, and alkyl bonds to the miscellaneous elements, and the other two, which are the alkyl bonds to the carbon and alkyl bonds to the oxygens. These are the others which are also the types of alkylation which we have discussed in the previous lecture. So during this alkylation there are so many products are produced. The one of the product is the lethal compounds, and the other is this mercaptans, which is generally used for smelling of LPG leakage. So these are the compounds which generally we use. There is some examples of these. So in today's presentation, the outline of today's presentation is what are the factor controls the alkylation. So the first one is the thermodynamics functions and mechanism reaction. This mechanism of vapor phase alkylation of hydrocarbons, mechanism of carbon oxygen alkylation, catalysis, concentration of reactants, temperatures, pressure, and energy required. So these parameters are affects the factor controlling the alkylations. So these factors are, the first we will discuss the thermodynamics. So the various thermodynamics functions such as the latent heat of vaporization, and which is the this free energy F and minus enthalpy H divided by temperature, or final enthalpy minus initial enthalpy, and this S is the entropy of the ideal gas at 1 atmosphere, and the physical properties like vapor pressure, viscosity, pressure, volume, and temperature relations has been tabulated for the most important hydrocarbons, including the paraffins and isoparaffins, olefins, and aromatics. So you have to know the tables of this, and by using that table you can easily calculate the heat of formation, and the formation can be calculated for the ideal gaseous state using that table, and the equilibrium constant for the reaction occurring in a commercial carbon alkylation process. So the first table is which is providing the value of heat formation and standard free energy of formation for alkyl benzene for the ideal gases state. So these are the different compounds: the benzene, toluene, ethyl benzene, orthoxylene, metaxylene, and paraxylene, and normal propyl benzene. These are some common compounds, and at different temperatures, 0 degree and 298 and 500 and 700 Kelvin. So this is the enthalpy, and this is the free energy at different temperature. So the values are given for the different component. So in the table 2 we will tabulated the value of equilibrium constant for the some reaction of benzene alkylation. So these are some reactions at different temperature. The equilibrium constant are given, which the temperatures are 298.16 500 800 1100 and 1500. So these are the different temperature and the equilibrium constant are given, and the reactions on the ethyl benzene and this n-propyl benzene, isopropyl benzene. So these are the different benzene compounds and normal alkyl benzene. So in many cases the reactions occurring during the carbon alkylation are sufficiently slow so that the equilibrium is not reached. The equilibrium constant are value of calculating the extent of reaction possible for a given set of operating conditions. This carbon alkylation are generally exothermic in reaction as shown in this diagram, and the reaction heat of reaction can be determined using the available thermodynamic and physical properties, and these heats are used in designing of reactor and auxiliary and heat exchangers. If you do not know about these components, the factor, the designing parameters, so you will get a high cost for your product. So the mechanism of the reaction, considerable research has been devoted to the studies to elucidate the mechanism and the characteristic of the alkylation reactions. Although the present information is not sufficient, but the mechanism of several commercial reactions has been determined with some. The knowledge of the mechanism is value for the developing kinetic equation which applicable a wide range of operating condition, and the planning research for process improvement and modifications. Now we will discuss about the mechanism for the liquid phase alkylation of hydrocarbons. So the either Friedel-Crafts or Protonic acid catalysts are often used when liquid isoparaffin or aromatic hydrocarbons are alkylated with olefins, and these catalysts are generally considered to be proton donator, which forms carbonium ion. So you can see how the protons are generated. So if you will see the acid here have a proton, and this is a base which generally taking these protons, and this is a carbonium ion. By the scheme you can see the basic reactions are probably similar for all catalysts, and the reaction temperature are all relatively close to the room temperature, about 40 to 30 degrees centigrade. The typical alkylation may be represented by the different series of reactions which are given here. The first reaction is when this olefins CH2 double bond CH2 in the presence of hydrogen chloride HCl plus aluminum chloride, then you are getting this carbonium ion and this anion, which is aluminum chloride, which is further anion is further react with this compound, and this is and there is the carbonium ion. So then you will get it another this carbonium ion you will generate it, and this is aluminum chloride negative plus CH2 you will get it, and further the chain is increasing as you are seeing in this reaction 3, and further it is also increasing, the 3A is showing, and this is the fourth reaction where you are seeing the chain is increasing and this product is forming, and this is again this carbonium ion is producing, and this aluminum chloride negative is there. The tertiary butyl ions forms during this reaction. This is a tertiary butyl ion in equation 4, which start another alkylation cycle 3A and 4. So although carbonium ions are presembles forms by all the usual catalysts, hydrogen fluoride, H2SO4 and aluminum chloride, which are the anions, will vary with the catalyst. And the role of hydrogen chlorides when used with aluminum chloride is to increase the acidity of the catalyst and hence make it more effective. The activity of boron trifluoride is increased by trace quantity of water or hydrogen fluoride. When the sulfuric acid is used as a catalyst, the concentration and the resulting acidity must be carefully controlled, and the side reaction such as the polymerization, isomerization, and this hydrogen transfer and destructive alkylation occurs during the catalytic alkylation of isoparaffin and aromatics with the olefins. All these reaction can be explained by means of the carbonium ion theory. In the case of polymerization, and carbonium ion such as in equation 1 and 3 reacts with the olefin, causing a chain growth, as you have seen in the previous 4 reactions. The polymerization is minimum by using relatively large axes of isoparaffins or aromatics. The normal paraffins are not alkylated satisfactorily using this catalyst. So the hydrocarbons, hydrogen atoms join to primary or secondary carbon atoms are apparently not labelized so easily as that attached to the tertiary carbon of isobutane, as you have seen in the reactions, in the 4 reactions. So the polymerization of the olefins is the main reaction. Certain side reaction also occurs between the catalyst and the hydrocarbons. For example, sulfuric acid partially oxidized hydrocarbons and release sulfur dioxide, especially at high acid concentration and high temperature. And this sulfuric acid alkylation are generally operated at low temperature than other alkylation. When the hydrofluoric acid is used as a catalyst, these alkyl fluorides are formed if the water content of the reactors become too high. So now we will discuss about this mechanism of vapor phase alkylation of hydrocarbons. The paraffins can be alkylated in the absence of catalyst at sufficiently high temperature, about 500 degrees centigrade, so that a small amount of the paraffins will decompose into free radicals. And the free radical mechanism for this reaction between propane and ethylene. So if you will see these two reactions, in the first reaction is this: when you will heat it at high temperature at 500 degrees C, so this free radicals, this CS3 plus is generated. This is a free radical, and which is reaction between the propane, this is a propane molecule, and which is reacting this free radical and generating this carbonium ion. So these are the isopropyl free radicals forms in equation 4. Start a new alkylation cycle. So this is a isopropyl radical. So when the propane reacts with the free radicals as in equation 2 and 4, the N-propyl radicals are sometimes obtained. However, the isopropyl radicals are formed predominantly. So as a result, the more isopentene is formed, this is a pentene group, is formed, and then N produce then N-pentene. In the side reaction occurring includes olefins polymerization, which also follows a free radicals path and produce high molecular weight hydrocarbons. So when the 1 to 3% of aliphatic halogenated compounds or nitro compounds is added to a paraffin olefin mixture, so that the alkylation reaction proceed at milder temperature, which is 300 to 400 degrees centigrade, and the substances that are effective have a relatively low thermal stability and form free radical at reaction temperature, and these free radicals further reacts as shown in equation 3 and 4, and these products obtained contains a chlorine atoms when a chlorinated initiator is used. So we have used the aluminum chloride as an initiator. So the product are similar to those in which no initiator are used. So these are some conditions for this vapor phase 1. And now the mechanism of carbon oxygen alkylation. The kinetic study have been made of reactions between the chlorinated hydrocarbons and the sodium or potassium alcoholates. The rate data indicates the second order equation between the reactants, and the phenol and substituted phenols were alkylated using this sulfonic acid esters. The rate of the reaction depends upon the these substituents on the aromatics rings, and the relative velocities was for the different components are suppose the p kerosene it is 1.58, and for the p2 naphthenol it is 1.46, and this phenol it is 1, and salicylic acid it is 0.3, and for the p chlorophenol it is 0.16, and in case of orthacrizole which is less than 0.12. So this para and ortho have a different relative velocities. So these are the different conditions which are used for this mechanism of the carbon and oxygen alkylation. So in today's discussion presentation, we have discussed the what are the different factors affects the alkylations, and these parameters are the thermodynamics functions and the mechanism of the reaction, and the mechanism of vapor phase alkylation of hydrocarbons, mechanism of carbon oxygen alkylations. So these four parameters we have discussed today for this, but in the next lecture we will discuss about the other factors, which are the catalyst, what are the different catalysts, and the concentration of the reactants, how this concentration of reactants affects this controlling the alkylation, and the temperature and the pressure, and what are the energy requirements for the system, as we have seen. And the some of reactions are the exothermic reactions. So these are the parameters which we will discuss in the next lecture. So thank you very much. If you have any query related to this topic, this topic is for the what are the factors which affecting the alkylation. So thank you very much. This is my email ID. If you have any query, you can ask me.